You've probably had some experience dealing with pendulums earlier in physics, but in this video I want to use the Lagrangian to find the equation of motion. So we'll just go through sort of the process and see how to use it, and then we'll talk about what we did toward the end. Let's try to write down the Lagrangian. So the Lagrangian L is equal to the kinetic energy T minus the potential energy U. So let's tackle these one at a time. Let's try to write down the kinetic energy for this problem. So in general, the kinetic energy is 1/2 the mass times the velocity squared. Now in this problem, since the mass at the end of the pendulum is actually following a circular path, it's more convenient to use polar coordinates than it is to use rectangular coordinates. So we're going to use theta here. And if we write the velocity in terms of theta in this problem, we'll get m/2, so 1/2 the mass, times the velocity. And to write the velocity in polar coordinates, we'll say the length times the time derivative of the angle. Right? So let's think through that. And we'll square that, right? Because it's velocity squared. So if this is traveling along a circle and there's a certain change in the angle, the arc length, the distance that the mass on the end has gone through, will be equal to the length of the string times the angle, if the angle is in radians, right? So L times theta is the distance, the arc length, and then L times theta dot, right? The derivative of the distance, or the change in distance, is the velocity, right? So length doesn't change with time, so the time derivative of L times theta is just L times the time derivative of theta, which is theta dot. So this is the velocity, right? So we've written it down in terms of convenient coordinates. So this is the kinetic energy term. And just to be consistent with my colors, I'm going to change these m's and make them green, like my picture here. So here's our T term. Now I'll write down the U term, the potential energy term. The potential energy term is, if this is a pendulum close to planet Earth where gravity is a constant, or the acceleration due to gravity is a constant, we can write that the potential energy is just the mass times the acceleration due to gravity, and these colors are more or less arbitrary just to make it look a little nicer, times the height. We'll use this purple for height. So mgh, right? This is the potential energy due to gravity of this pendulum. So how do we write h in terms of theta? Well, if the pendulum has swung out to a certain angle, right? Maybe this angle that's drawn here. The height is this. So the height could be thought of, or one way to think of the height is this distance here. So if we're calling our 0 point of height, or our 0 point of potential energy, at the bottom of the arc here, so this is the 0 point, the height at any angle will be this distance here. So what is this distance in terms of theta? Well, as is often the case, we can say, hey, look, we found a right triangle here, so we can use our knowledge of trig functions to solve this triangle and find these distances. So what is this? Well, we know that the distance, this distance here from the point where the string is fastened to the bottom of the arc, is just L, right? This whole thing here, maybe I'll just draw this out. This is L, right? And so h is going to be L minus this part in here. So we'll make this orange. So this part here, so if we can find what this part is, subtract it from L, we'll get h. And now since this is a right triangle, we can say that this side is L times the cosine of this angle, right? This is the hypotenuse, L is the hypotenuse, this is the adjacent side, the side adjacent to this angle. So we can say that this is L cosine theta. So I'll draw, well, I'll write out this whole equation, right? L equals this minus whatever we're going to find next. So let's see. So I'll write m, g, and then h is just L minus L cosine of theta. I'll use orange. Right, so we've written out this Lagrangian in terms of theta. This is the kinetic energy, this is the potential energy. We can see it kind of makes sense that the kinetic energy, even though we've changed coordinates, it's still, the kinetic energy still depends on the time derivative of our coordinate, and the potential energy still depends just on the coordinate itself. And I'll just factor out this common L term here just to make it look a little bit more neat. So I'll rewrite it. So this term here is actually, we see something kind of interesting that pops up a lot in physics. We actually have this mgl here. This has units of energy. So these constants out here make it so that this thing is energy, and all of the geometry of the problem is contained in this unitless thing right here. So that's just sort of a side note, but as you go further in physics, you'll see that a lot, where everything sort of, where all the relevant physical constants are just sort of thrown out in front, and then we're left with something that's dimensionless that contains sort of the details of the geometry or the arrangement of the particles. But anyway, if we plug this into our Euler-Lagrange formula, so we have dl d theta, right, and I might as well keep making my thetas orange, minus the time derivative, the full time derivative, whoops, I always do that, d dt of the derivative, the partial derivative with respect to theta dot, of the Lagrangian. All of this equals 0. All that equals 0. So let's scroll down and actually see what this turns out to be. So for this term, we're taking the partial derivative of L with respect to theta. So this term right here, since we're doing a partial derivative, we don't actually have to worry about this, right? This is theta dot. So theta and theta dot are related, so we might have to do some chain rule business here if this were a full derivative. But since it's only a partial derivative, we're only concerned with how L changes explicitly with theta. And that just means when theta shows up all by itself. We're not concerned with how theta changes as time changes. We're just concerned about what theta is sort of right at this moment. Right? This is like the potential energy. It only depends on the position, not the rate of change of the position. So it's analogous to that. So if we take this derivative, we'll see that this term here, if we distribute this mgl times 1, this will just be a constant. Theta is not in here, so the derivative is 0. So we can forget about this one, and we can write mgl m times g times l, right? And then we're left with a positive cosine theta, right? This negative here, and we distribute that, and this negative here, those two negatives cancel out, and we get a positive. So we're basically taking the derivative of positive cosine, and we end up getting negative cosine, oops, not cosine, negative sine theta, right? Negative sine theta. So that's this term. Now we can move on to the other term. So let's first do the partial derivative with respect to theta dot of L, right? So for the same reason, we can disregard this, right? We're only concerned with the time derivative as it appears in L. So when we take the derivative of just this term, we get m over 2, or I'll just write ml squared over 2. And then when we take the derivative of theta dot squared, all we get is 2 theta dot, right? If we just think of this as x and we take the derivative of x squared, the derivative of x squared is 2x, right? So we're taking the derivative with respect to theta dot of theta dot squared. We just, a 2 pops out and it's to the first power. All right, so we'll write 2 theta dot. And then all of this together equals 0. I'll do a few things here. I'll make these positive, right? Because it equals 0, so we can just think of it as putting them on the other side of the equation, or multiplying by -1, or whatever, however you like to think about it. These negatives we can just make positive. And then these 2's cancel, right? So these 2's will cancel, right? These will become positive, these negatives become positive. And then we can divide both sides of the equation by m. So these m's go away, and then 0 over m is still 0, so we don't need those. And then I'll also cancel one of these l's, right? There are 2 l's here, and there's 1 l here. So we'll divide both sides of the equation by l. 0 divided by l is still 0, and then we have 1 l left here. So I'll rewrite it over here. So I can write g times the sine of theta plus L. Oh, I forgot. So I took the derivative with respect to theta dot here. So we came up with this 2 theta dot. Now we're taking the time derivative of this whole thing. So the time derivative, right, this is just the second time derivative, because all of this is constant with time. So we have theta double dot. So I forgot a dot. So there are 2 dots here, right? So now we have L theta double dot. And this all equals 0. So if you remember the equation of motion for a pendulum, we get this theta double dot, right? This is like the acceleration is equal to g over L. So g over L times the sine of theta. Right, and if we want, we can say we're restricting this to small angles, so sine theta is approximately equal to theta for small angles. And we can say, so a squiggly equals approximately equal to g over L times theta. And with this simplification, this small angle approximation, we actually end up getting the equation for a simple harmonic oscillator. So by using the Lagrangian, we were able to solve this problem without having to think about force vectors. And this problem is still simple enough where thinking about force vectors is still doable, and you've probably actually solved this problem before using force vectors. But I think it's good to see this process carried through with something that you already more or less understand.